All right, we're starting topic 14. In this topic, we're going to be looking at, or in this block, applying the Pythagorean theorem and using it to find unknown sides of right triangles and also to determine whether or not a triangle is a right triangle. So, first of all, we need to make sure we understand what a right triangle is, and we should know at this point that just means it's a triangle that contains one right angle. Remember, a triangle cannot contain more than one right angle since the three angles have to add up to be 180 degrees. So if you have a right angle, that leaves 90 degrees for the other two. So obviously you can't have a 0-degree angle, so one right angle is the most that you can have. So how can we classify right triangles by their side lengths? So right triangles can be either scalene or isosceles. Remember, scalene means none of the sides have the same length. Isosceles means two of the sides have the same length. A right triangle cannot be equilateral because remember, all equilateral triangles are acute. All three of the angles must be 60 degrees in an equilateral triangle. So how can the Pythagorean theorem be used on right triangles? Well, it can be used if you know two side lengths to determine the third side length, or if you are trying to figure out whether three lengths can be a right triangle or not. So those are the two ways that we're going to be looking at it today. So when we are solving for unknowns using the Pythagorean theorem, a lot of times we're going to end up with what is called a radical. And so a radical is just a number that contains a square root symbol. You'll have other roots that you can take in higher math, but at this point we're just taking square roots. So as a review, I have here in purple the perfect square numbers all the way up to 20 squared. So remember, perfect squares are just when you take a number and multiply it by itself. So we have 1 squared is 1, 2 squared is 4, 3 squared is 9, and all the way up to 20 squared is 400. These are really the ones that you should have memorized. These are the most common perfect squares that you'll encounter. I'll be honest, when we get up to 18 and 19 squared, I really don't have those particularly memorized, but the rest of them occur so often that I do. So we're just going to simplify each one of these radical expressions, and it says without a calculator, and really all that means when it says without a calculator is that you're not just going to simply type these in and write down what the decimal is. You will only use decimals for radicals if you are given rounding instructions, because when you take the square root of a non-perfect square, you get an irrational decimal, meaning it goes on forever without a repeating pattern. So you're not just going to decide yourself, I'm going to round to the nearest tenth or the nearest hundredth. If you're not given rounding instructions, that means you're supposed to give the most exact answer, not an approximation. So 225 is our very first one, and you can see that that is in our list of perfect squares right here. So 225 is a perfect square. You can count up here if you don't know. Surely you know 144 is 12 squared, so that's 13 squared, 14 squared, 15 squared is 225. So 225 is one of our perfect squares. If I was on my calculator to put the square root of 225, it would not give me a decimal answer. It just gives me 15 because it is a perfect square. So the square root of 225 is exactly 15. Now, 48 is not in our list of perfect squares. You can see it would be somewhere between 36 and 49. The square root of 36 is 6. The square root of 49 is 7. So the square root of 48 is somewhere between 6 and 7, and obviously closer to 7 than it is 6. So if we put in the square root of 48 in our calculator, it is an irrational decimal, 6.9282033, and that's even rounded in that position right there. It goes on forever. So since we're not given rounding instructions, we are not going to give the decimal answer, but we can still simplify it. So giving an answer as square root of 48 would be like giving an answer as 3 over 6. That is not a simplified answer, so you want to give it in its most simple form. So if you know your multiplication facts well, then this is pretty easy. You can think about all the numbers that multiply to get 48. For example, we have 1 and 48, we have 2 and 24, 3 and 16, 4 and 12, 6 and 8. Those are all the pairs of numbers that multiply to get 48 that are integers, right? We don't want decimals. So we're looking for perfect square factors, and even though 1 is a perfect square, if I replace 48 with 1 times 48, that really didn't help anything. I still have the 48 under the radical. So my next factors are 2 and 24. Neither one of them are a perfect square. Then we have 3 and 16. 16 is a perfect square. So I'm going to replace the square root of 48 with 3 times 16 because 16 is a perfect square. And so I can take the square root of 16. Now when it comes out of the radical, it doesn't come out as a 16 because you're taking the square root of it. So the square root of 16 is 4. So I would have a 4 outside and a 3 inside. So we would say that's 4 square roots of 3. Or in other words, that's 4 times the square root of 3. Now I can go back to my calculator here just to check that. I know it's a little hard for you to see on the screen here, but I still have in the square root of 48, and that's 6.2928, blah, blah, blah. Well, if I put in 4 square roots of 3 into my calculator, I hope you can tell that's exactly the same decimal. And so that lets me know that these are equivalent, just like 3 over 6 is equivalent to 1 over 2. Now always double make sure that you do not leave a perfect square factor underneath the radical. The only factors of 3 are 1 and 3, and again, even though 1's a perfect square, that would not simplify. And the reason why I tell you that is a lot of students will replace the square root of 48 with 4 times 12 and take the square root of 4 and bring it out as a 2 and give their answer as 2 square roots of 12. And even though these are equivalent, the square root of 48 is equivalent to 2 square roots of 12, that is not simplified all the way because 12 still contains a perfect square factor. You could replace 12 with 3 times 4, so you're just not done at that point. You're going to replace 12 with 3 times 4, take the square root of 4, bring it out as a 2, and it has to multiply with the 2 that's already out there, and again we get 4 square roots of 3. So just be careful to make sure that you have reduced all the way. It would be like saying 6 over 12 is equivalent to 3 over 6. That's true, it's just you haven't simplified it all the way. So never leave a perfect square factor underneath your radical. Now, one thing, even though it says without a calculator, you can use your calculator as a tool. So, for example, if I'm trying to simplify the square root of 54, I can go to my y equals, let's see, and put the number underneath the radical, which is 54, but I'm not putting the radical in the calculator. I'm just putting the 54 divided by x in my y equals, so that says 54, I don't know if you can see that, 54 divided by x and under my y equals. And you're going to go to the table. So when you're going to have to hit second graph on yours. I'm just going to table here, and I'm going to actually start my table at 0 so I don't have to do all that scrolling. So now I can see the factors of 54 are 1 times 54, 2 times 27, 3 times 18, I don't want these decimals, 6 times 9, and so on. And remember, I'm looking for perfect square factors, and I don't want 1. So 2 and 27, neither one are, 3 and 18 are not, but 6 and 9 contain a perfect square factor of 9. So I'm going to replace the square root of 54 with the square root of 6 times 9 and take the square root of the 9 and bring it out as a 3. So this would be 3 square roots of 6. So on part D, we could go back to our y equals. Instead of 54 divided by x, I'm going to put in 135 divided by x. Look in my table. I see 1 times 135, which is not helpful. 3 and 45, neither one are perfect squares. 5 and 27 are not. The next one is 9 and 15. That's what I want because 9 is a perfect square. So I'm going to rewrite the square root of 135 as the square root of 9 times 15. The square root of 9 is 3, so that comes out as a 3 and leaves the 15 under the radical. 15 does not have any perfect square factors because the only numbers that multiply to get 15 are 1 and 15, 3 and 5. And again, the 1 would not be helpful. Now, I know we took a lot of time going over that, but that's going to be super important with the next couple of topics. We're going to have a lot of radicals that we're going to have to simplify. So that's definitely a skill that you need to get perfected in order to do well in the next couple of topics. All right, so let's move on with the Pythagorean theorem. By the way, one of our math teachers went to Greece and found out that in America we pronounced that wrong. Instead of Pythagoras, the one that is noted for coming up with this theorem, his name is really Pythagoras, so this is really the Pythagorean theorem, but I will just stick with Pythagorean if you don't mind. All right, so it's one of the most useful theorems that we use in geometry, and you've probably studied this before, hopefully even last year in Algebra 1. So we're going to review this animation to help us re-familiarize with the Pythagorean theorem. So the Pythagorean theorem, as you know, as a squared plus b squared equals c squared, is really, in terms of what these variables represent, the a and b are the legs of a right triangle, so they are the sides that make up the right angle together, and c is always the hypotenuse, which we know is the longest side of the right triangle. It's across from the biggest angle, the 90-degree angle. So a and b are the legs, c is the hypotenuse. Whoops, clicked the wrong thing there. All right, so what you can see here is they've actually put a square on each one of the sides of the right triangle. So this leg A is a side of the squared. Every side has a length of A, and so the area of that squared would be A times A, which is A squared. And we did the same with B and the same with C. And so one way that we state the theorem is that for any right triangle, the square of the hypotenuse, and that's literally the square made by making the hypotenuse all four sides of it, is the sum, which means to add, of the squares of the legs. So a squared, the square on A, plus b squared, the square on B, is equal to the square on the hypotenuse. And so we want to make sure we understand the concept and not just have it memorized as a squared plus b squared equals c squared. So the sum of the two smaller squares is always going to equal the largest square, which is the one on the hypotenuse. Now, what we're going to see is a visual of this theorem. And so this is the a squared, and here's the b squared, which they have divided into 4 parts here. And so what we're going to actually show is that when we put these pieces together, they will fit perfectly inside the c squared box. So I'll just show that to you by placing these in the right place. This goes here. So there's my b squared inside there. Here's my a squared that fits perfectly here. And so that just shows us a model view of a squared plus b squared actually equaling c squared. Now I can adjust the size of the sides of this right triangle, and you can see that that still holds true. So it's not that we just had this perfect one that it worked on. It works for any right triangle. Now the next visual is just showing you that as long as you have similar figures on A, B, and C, it really doesn't matter what shape you put there. The a squared plus the b squared is always going to equal the c squared. Whatever the shape is on A plus the shape on B will equal the area of the shape on C, as long as they are similar and in relation to those sides of the right triangle. All right, so let's X out of that and move on. So on number 2 in your notes, it said to state the Pythagorean theorem in words and using the algebraic equation. So again, I think you guys have the algebraic equation memorized, and it is simply a squared plus b squared equals c squared. But you want to make sure you know how to state it in words. And so again, in words, it would say in a right triangle, the sum of the square of the legs is equal to the square of the hypotenuse. So in a right triangle, the sum of the square of the legs is equal to the square of the hypotenuse. And we're not doing the tracing on number 3 or the cutting. You can certainly do that on your own if you would like to show that, but I showed you that visually on the animation. All right, so we'll pick up with number 4 in your notes in the next video.